Okay, our last topic for the forces unit is center of mass. And this is something that I think you should know about right now, but it's not going to apply very heavily to what we do until the end of the year. We'll talk a little bit more about center of mass and related topics towards the end of the year. But you should still understand what it is at this point, and it is important to know. So when we talk about center of mass, what we're essentially talking about is the mathematical average. I'll put that in quotes. Of the location of mass in an object. The mathematical average of the location of mass in an object. In other words, if you were to somehow put an object on a grid, like an XY plane, and plot out the location of every piece of mass, and then take the average of all those locations, the center of mass would be what you get, the average. Another way to think about it is the location where gravity acts from on average. You can think of each of those little individual pieces of matter all having a force of gravity on them, or what's more useful to us is to assume and is for us to assume that gravity acts specifically from the center of mass. Because otherwise, I mean, for any extended object, like for this pen, for instance, gravity doesn't act on just one part of it. Gravity acts on all the parts of it. And that would be a lot of, little tiny FG vectors. Instead, what we do is we find the center of mass and we say, on average, gravity acts from this point, and we only deal with gravity acting from that point. So let me just draw you some pictures of center of mass. Some shapes it's very easy to find the center of mass from. For example, this square. Pretty obvious, the center of mass is right about there, right in the middle. Something a little bit trickier might be this triangle. It might look pretty obvious at the outset. You might say, well, it's probably about halfway up the triangle. But if you think about it, more of the triangle's mass is down here, closer to this lower bottom edge than it is towards the top. So that's going to shift the center of mass not to be mid-height on the triangle, but down a little bit, probably right about here. Okay? So again, it's the average of where the mass is. And there is a formula for calculating where center of mass is for a system of objects. We're not going to get into that right now, I don't think. But, I mean, it is possible to do. Let me give you some other shapes. This is not a circle, but a donut shape. And for this shape, it's kind of interesting. The center of mass is actually outside of the object itself. It's in the middle of the donut hole, if you think of it that way. And you can even have like kind of a weird shaped object like that. And the center of mass would be, again, in the average spot where the mass would be. So I'd say for this, it's kind of extended down and to the right, so maybe your center of mass is right about here or so. Okay? So conceptually, it's not too hard to understand. Now, what do you need to know about the center of mass for now? There's a couple different things. First of all, forces acting near an object's center of mass usually do not cause it to tip or spin as easily as forces acting farther from, and I'm going to abbreviate here, the center of mass. COM is an abbreviation for center of mass sometimes. So forces acting near an object's center of mass usually don't cause it to tip or spin as easily. Now, we haven't really talked about any of this tipping or spinning motion. We will towards the end of the year when we talk about torque and rotational motion. But for all you need to know right now is that if a force acts near the center of mass, usually it doesn't cause it to tip or spin as easily as forces acting farther away from a center of mass. Next, for complex objects or systems, collections of objects, the center of mass typically shifts to be closer to the majority of the mass. So for instance, this object here that's kind of weird looking, if I were to, let's say, chop off this right hand side, the center of mass would shift to be near to the rest of the mass that's left. So it would probably shift about, maybe a little down and to the left a little bit. Okay, let's see here. The last thing is that more support tends to be needed near the center of mass to hold something up. And that's just kind of a general statement, but more force, more support is usually needed closer to the center of mass to hold something up and cause it to not spin or rotate. Okay, I actually have one other topic to talk about, and this is a little bit more important, and you guys will get a kick out of this, in that I have actually been lying to you for the past year and a half or so, a year and a little bit. And I should clarify, I haven't been lying to you, I guess I just haven't been telling you the full truth. We're going to talk a little bit about Newton's second law right now. You guys are used to saying that Newton's second law, it's the one with the equation, is F net equals ma. And that's actually not the full picture. It's that the net force is equal to the mass times the acceleration of, not the entire body, the acceleration of the center of mass. Now, we haven't had to clarify this before because we don't really care, or we haven't really talked about objects that can't be reduced down to a single point. Okay, we haven't talked about these extended long objects really. But if you think about it, like, think about the human body. Different parts of objects can have very different accelerations. For example, imagine, if you will, like a high diver, like a diver diving into a pool, and they're doing all sorts of spins and flips and tucks and turns as they go down. As they fall, as they rotate and fall, different parts of their bodies are undergoing much, much different accelerations. Okay? So their feet might be tucked in, or let's see, for example, they might, sometimes, like in a certain case, their feet might be tucked in. They might have their arms out to the side or something, or arms up above their head, and therefore, when those different parts of their body are moving and falling, as measured from the ground, they would have different accelerations relative to the ground. What won't change is the acceleration of their center of mass. That is the acceleration that we are finding when we use the net force, when we use Newton's second law, when we use net force equals ma. It's the acceleration of the center of mass. So, different parts of objects can have very different accelerations. However, a net force on an object or system has a distinct relationship with that object or system's center of mass. Okay? The individual parts of the object can have very widely different accelerations, but the center of mass of that object or system has the acceleration that you would find by using Newton's second law. Okay? Newton's second law will give you the acceleration of the object or system's center of mass. So, two corollaries to that. If the object's center of mass is not accelerating, if it doesn't accelerate, then there must be no net force on the object. So in other words, if I stand up and I flap my arms about and kick my legs, but if my center of mass doesn't accelerate from that spot, the net force on me should still be 0. My arms and legs can accelerate, but unless my center of mass accelerates, there's no net force on me. Without a net force, this is the other part of that, the center of mass can't accelerate even if parts of the system do accelerate. Okay, so Newton's second law gives us the acceleration of the center of mass, not the acceleration necessarily of any other part, okay, the acceleration of the center of mass. If the center of mass is not accelerating, there's no net force on the object. If there's no net force, likewise, the center of mass cannot accelerate even if parts are accelerating. Okay, it's a little bit hand wavy. We don't deal too much with it, but it is good for you to know. We'll talk more about center of mass in some future units. This is the end of the forces unit. I'll talk to you again when we get to our next unit.